up until this point, we have been working with simulated distributions. So we put in Rossmann chance and we simulate what it would or could look like if the null hypothesis is true. Now we're moving to theoretical distributions. And what is important is that if we take a sample size large enough, we can count on it behaving in very predictable and repeatable ways. And that's really what the central limit theorem is all about. A few things that come out of it. We say that the mean or the center of that sampling distribution becomes equal to the parameter of interest. Okay, equal to. So if we're dealing with categorical data versus quantitative data, for quantitative data, the center will become equal to mu. If we're dealing with categorical data, the center of the distribution will become equal to pi. The second thing that comes out of it, instead of having to deal with the simulated distribution to tell us the spread or the standard error, we can count on some theoretical behaviors. So the standard error or the spread of that sampling distribution, it's different if we're talking about categorical versus quantitative. If we're talking about categorical data, this is what we're looking at for the spread or the standard error or the standard deviation of the distribution. If we're talking about quantitative data, the spread of the distribution is sigma divided by the sample size, the square root of the sample size. And why is that? Well, the shape of both of these distributions, that's the third thing that comes out of the central limit theorem. The shape, if we take a large enough sample size, becomes bell-shaped, regardless if it's quantitative or categorical. The thing is that they're shaped just slightly different. Okay, bell shape just means that we have a center. Our mean is in the center. Okay, in this case, this would be mu. This would be pi. They're both symmetrical about the mean. So we have exactly half above and below. And if we folded it across the mean, both sides would flip, would fall right on top of one another. When we're talking about categorical data, we call it the standard normal distribution or the Z distribution. When we're talking about quantitative data, we're talking about the T distribution. Okay? And because they're shaped slightly differently, the spread is just slightly different. We can see that this has fatter tails as compared to categorical data. So that means that the standard error or the standard distribution is slightly different. That's why we have a Z-score for categorical. We have what we have call a T-score for quantitative. And here's just them overlaid. You can see the difference between them. They're both centered about the mean, and they're both symmetrical. They're both bell-shaped, but they're just slightly different in shape. Okay. So let's talk about how we generated this. So here's a data set from our written homework where we had the mean age of 1,175 students. This was one of the written homework problems. And this is our population here. And I can see that the mean of this population is 16.44. So if I take a sample of this 1,175 students. Let's take the sample size of 5. And then let's just take one sample first. This is one X bar. The computer selected randomly 5 of these 1,175 data points. They're all ages 18, 18, 18, 19, 18 divided by 5 to come up with a mean of those 18.2. That's an X bar. Okay, so if I have my sample size 5, let's say I do 10,000 of those. And I draw those samples. This. I can see that this, it kind of looks like my distribution. Notice this distribution is skewed, so it's not symmetrical. So my starting data is not symmetrical. And so if I take sample size 5 and I take that 10,000 samples, this is my distribution here. Doesn't look very symmetrical. It does actually have a mean 18.644. That's the same here. Let's take a bigger sample. Let's take a sample of 20. Sample size of 20. So now look what's happening. It's looking a little bit more symmetrical. If I take a sample size of 50, you see how it's becoming more and more bell-shaped? If I take a sample size of 100, it's becoming even more and more bell-shaped. So it's starting to look like, as the sample size gets bigger, something that is bell-shaped and that we can predict better. Let's do one more, 200, see what happens. Okay, so down here, this looks even more normally distributed. If I just put this over top, you can see it's very, very symmetrical. Okay, and I can actually see the mean here is equal to 18.644, which was my original data. So that what's interesting here is that even though my original data is skewed, if I take big enough sample size and then repeat it, this distribution of sample statistics becomes normally distributed. All right, so let's go back and compare this. I've got here a cut and paste view. So here is where I had a sample size of 5. I can see this does not look very symmetrical, right? And I can see that my mean is 18.649 versus my data, my population data, which is 18.644. So it's close, but it's not exact. The bigger my sample size, okay, the mean gets closer, starts to look a little bit more symmetrical. And what I also want you to notice is that the spread of the data, here I go from about 18 to maybe 21. Okay, here I go from 18 to about 20. Okay, now if I take a sample size of 50, I notice that my mean is exactly equal to my population of 18.644. This is looking more and more bell-shaped, okay? And my standard deviation is getting smaller and smaller. So up here, my standard deviation was about 5.37, okay? Then when I went from a sample size of 5 to 10, my standard deviation got smaller, meaning the data is less spread out, it's less dispersed. When I come down here, sample size of 50, my standard deviation is even smaller, 0.167. We come over here, sample size of 100, standard deviation even smaller. Okay, so my data is getting more and more compact here. Okay, this is going from about 18.3 to 18.9, and it's starting to look really normally distributed, and the mean is, or the center of the data is approaching exactly my mu is equal to 18.644. If I impose or overlay the normal distribution, we can see how that looks here. So the bottom line here is that whether I'm dealing with categorical data or quantitative data, if my sample size is big enough, okay, in the case of categorical data, if my successes are greater than or equal to 10 and my failures are greater to 10, this means that n, success plus failure, has to at least be greater than 20. Same thing here for quantitative data. So this says the data can't be skewed. My example, the data was skewed, and in fact, it's got to be a bigger sample size if you have skewed data, but we're not going to be dealing much with skewed data. So long as I take a sample size of 20, that will let me be able to use the theory-based approach so I can figure out the spread. I know that my center is going to be equal to my population parameter. And let's just recap. So if I take a big enough sample size, then my mean, or the center of my distribution, is going to equal my parameter. equal my parameter, whether it be mu or pi. The spread of the data, if it's categorical, my standard error, this is one standard error, one standard deviation is this. If I have quantitative data, this is my standard error or my standard deviation or my spread of my distribution is sigma over square root of the sample size. So I can create a standard distribution. It will behave in a very predictable way.